What if everything we think we know about the beginning of the universe is just the tip of an unimaginable iceberg? Picture the very first moments of existence, not as a single, definite event, but as a swirling, uncertain dance of possibilities, where reality itself existed in multiple states at once. This isn't science fiction. It's the mind-bending world of quantum mechanics, where particles can be in two places at the same time, where cause and effect don't always follow the rules we expect, and where the universe might have begun not with a bang, but with a quantum superposition, a cosmic coin flip that set everything into motion. Think about that for a second. The entire cosmos, all the galaxies, stars, and planets, even time and space themselves, might have emerged from a single, unfathomable moment of quantum uncertainty. It's a concept so strange that even the greatest physicists struggle to wrap their minds around it. Yet, hidden within this mystery are clues that could rewrite our understanding of reality. Today, we're diving into 30 astonishing theories about the universe's first quantum superposition, ideas that stretch from the edges of theoretical physics to the bleeding frontiers of cosmology. Some of these theories sound like they're straight out of a dream. Others might just hold the key to unlocking the deepest secrets of existence. So why does any of this matter? Because if we can grasp how the universe began in a state of quantum ambiguity, we might finally answer questions that have haunted humanity for millennia. Where did we come from? How did something emerge from nothing? And most tantalizing of all, could there be other universes, other realities, born from different outcomes of that first quantum split? The journey we're about to take isn't just about equations or abstract concepts. It's a quest to understand the very fabric of reality, to trace the threads of existence back to their shimmering, uncertain origins. Strap in, because by the time we're done, you might never see the cosmos the same way again. The first theory takes us back to the very instant of creation, but not as the Big Bang we usually imagine. Instead, picture a cosmic game of chance, where the universe itself was born from a random jitter in the fabric of nothingness. This is the idea that our entire reality might have sprung from a quantum fluctuation in an otherwise empty void. Think of it like a bubble forming in a perfectly still pond, except this bubble contained all of space, time, and energy we know today. At the heart of this theory lies zero-point energy, a strange feature of quantum physics where even in a complete vacuum, particles flicker in and out of existence. These tiny, fleeting bursts of energy are normally too small to notice, but under the right conditions, they could have triggered something far grander. Some physicists suggest that in the extreme environment of the early universe, one of these quantum fluctuations didn't just vanish, it expanded violently, becoming the seed of everything. What's wild about this idea is how it turns classical cosmology on its head. Instead of a singular, definite beginning, the Big Bang becomes more like a roll of the dice, a random event in an endless sea of possibilities. It means our universe might not be the only one. If one quantum fluctuation could create everything we see, why couldn't others do the same? This opens the door to a multiverse where countless other universes might exist, each with its own laws of physics, born from their own quantum ripples. But here's the real kicker. This theory doesn't just change how we think about the past. It forces us to question what nothingness even means. If a universe can emerge from empty space, then nothing might not be as empty as we thought. It's a humbling reminder that the rules governing reality at the smallest scales could rewrite the story of the cosmos itself. What if the birth of our universe wasn't a solitary event, but the explosive aftermath of a cosmic traffic accident? The multiverse collision hypothesis paints a picture where our reality wasn't born from nothing, but from the wreckage of two or more universes slamming together in the vast expanse of a higher dimensional multiverse. Imagine two soap bubbles floating in the air, gently drifting until they touch and merge into a single, rippling sphere. Now replace those bubbles with entire universes, each with their own laws of physics, colliding in a cataclysm so immense it created the quantum superposition that birthed everything we know. This idea takes the strange predictions of quantum mechanics and scales them up to cosmic proportions. Just as particles can exist in multiple states until observed, entire universes might have coexisted in a blurred superposition until their collision forced one outcome into existence: our reality. The energy released in that impact could have been the engine behind cosmic inflation, that brief but unimaginably rapid expansion of the early universe. Suddenly, the mystery of why everything flew apart so quickly in the first moments after the Big Bang starts to make sense. It wasn't just expansion, it was the shockwave of a multiversal fender bender. Some versions of this theory suggest these collisions might not even be rare events. If the multiverse is infinite, then universes could be constantly bumping into each other, each collision creating new cosmic bubbles with different physical laws. Our universe might just be one of countless others in an endless cycle of creation and destruction, a single note in a symphony of colliding realities. Even stranger, traces of these collisions might still linger in the cosmic microwave background, the afterglow of the Big Bang, like faint bruises on the fabric of spacetime. But here's where it gets truly mind-bending. If this hypothesis is correct, then the very laws of physics we take for granted, the speed of light, the strength of gravity, might not be fundamental truths, but simply the frozen accident of how our particular universe collision played out. Other universes born from different crashes could have entirely different rules, some where time flows backward or matter behaves in ways we can't even fathom. It's a humbling thought. Our entire reality might just be the fallout of a quantum accident in a much bigger, much weirder multiverse. Now imagine peeling back the layers of reality to reveal something even stranger. What if our entire universe, with all its vast galaxies and swirling nebulae, is nothing more than a projection, a cosmic hologram? This is the radical idea behind the holographic principle, which suggests that the three-dimensional world we experience might actually be encoded on a two-dimensional surface at the very edge of the cosmos. And if that's true, then the universe's first quantum superposition could have been less like a physical event and more like a flickering image forming on some unimaginable screen. The roots of this theory stretch back to an unexpected place: black holes. When physicists studied these gravitational monsters, they stumbled onto a paradox. According to the laws of thermodynamics, information can never truly be destroyed. But if something falls into a black hole, it seems to vanish forever. The solution: the information isn't lost, it gets smeared across the black hole's event horizon, the point of no return, like a message etched onto a celestial billboard. From there, the leap to the holographic principle was almost inevitable. If a black hole's information can live on its surface, why couldn't the entire universe work the same way? This means the Big Bang might not have been an explosion in three-dimensional space, but a quantum fluctuation on a flat, two-dimensional boundary, a ripple in the code of reality itself. Think of it like a movie projected onto a screen. The images look three-dimensional, full of depth and movement, but they're all generated from a flat surface. In the same way, our universe's staggering complexity, every star, every planet, every conscious thought, might just be data shimmering on some primordial surface we can't even see. The implications are staggering. If the holographic principle is correct, then the quantum superposition at the beginning of time wasn't happening in the universe. It was the universe, a flickering uncertainty in the cosmic code. It would mean that everything we experience, from the force of gravity to the passage of time, is just a shadow of deeper, more fundamental processes playing out in a reality we can't access. And here's the real twist: this could solve one of the biggest mysteries in physics: how to unite quantum mechanics with general relativity. If spacetime itself emerges from quantum information, then the two theories might just be different ways of describing the same holographic illusion. But the weirdness doesn't stop there. If the universe is a hologram, then the past, present, and future might not be as fixed as they seem. Just like a computer can rewind a video, the cosmic code could hold multiple versions of history in superposition until played back. It's a dizzying thought that the moment of creation might still be unfolding, not as a linear event, but as a cosmic algorithm resolving itself into the reality we know. And somewhere on the edge of everything, the universe's first quantum flip might still be waiting, frozen in the ultimate buffer between existence and the void. We've seen how the universe might have emerged from collisions, holograms, or quantum bubbles. But what if spacetime itself was born from something even more fundamental? Enter loop quantum gravity, a theory that rewrites the cosmic rulebook by suggesting the fabric of reality isn't smooth and continuous, but stitched together from tiny, indivisible threads. Picture the universe not as a vast, flowing river, but as a shimmering web of interconnected loops, each one a quantum of space itself, vibrating with potential. At the heart of this idea are spin networks, intricate structures where space and time dissolve into a dance of quantum connections. Imagine a cosmic spiderweb, but instead of silk, its threads are woven from pure geometry, tiny loops of gravitational field, each carrying a discrete chunk of space. In the beginning, these loops didn't have a single, defined state. They existed in a dizzying superposition, a quantum haze where every possible configuration of spacetime flickered in and out of existence simultaneously. Then, in a moment of cosmic crystallization, one configuration snapped into place, giving birth to the universe as we know it. This isn't just poetic imagery, it's math with radical implications. If loop quantum gravity is correct, then the Big Bang wasn't the start of time, but a phase transition like ice melting into water. Space and time didn't emerge from nothing. They condensed from a foaming quantum sea of spin networks, resolving from infinite possibilities into a single, stable reality. It means the universe might be pixelated at the smallest scales, with a fundamental graininess to spacetime itself. The consequences ripple outward. A discrete universe would rewrite our understanding of black holes, where singularities, those infinitely dense points at their cores, might just be knots in the spin network too tight to unravel. Even the arrow of time, that relentless march from past to future, could emerge from how these quantum loops entangle and evolve. And here's the real kicker. If spacetime has a smallest possible size, then there's no such thing as true nothingness, just a seething quantum substrate waiting to crystallize into new universes. Yet for all its elegance, this theory forces us to confront a haunting question. If reality is woven from quantum threads, then what weaves them? Are the spin networks the final layer of existence, or is there something deeper still? A loom beyond spacetime, humming with the potential for infinite cosmic tapestries? The answer might lie in the universe's first quantum shiver, a tremor in the spin networks that still echoes in every atom, every star, and every thought we've ever had. What if the universe needed a witness to exist at all? This is the startling premise behind John Wheeler's participatory universe theory, which suggests reality itself might have remained a blur of quantum possibilities until the first act of observation collapsed it into being. Wheeler, one of the 20th century's most visionary physicists, took the strangeness of quantum mechanics, where particles don't settle into definite states until measured, and scaled it up to cosmic proportions. In his view, the Big Bang wasn't just the beginning of time and space. It was the moment the universe chose its own reality through an observer's gaze. Think of it like a cosmic version of the double-slit experiment, where particles behave as waves until someone looks at them. On the grandest scale, the entire early universe could have existed in a hazy superposition of countless potential states, different laws of physics, different configurations of matter, until some primordial act of observation locked one version into place. But here's the twist. In Wheeler's framework, there was no external observer. The universe observed itself. It's as if reality bootstrapped itself into existence by creating observers who would then define it. A dizzying loop where life and cosmos depend on each other in ways we're only beginning to grasp. This idea forces us to confront quantum mechanics' infamous measurement problem head-on. Why does observation have such power over particles? Why does reality seem to crystallize only when we look? Some interpretations suggest consciousness plays a role, that mind and universe are entangled in ways classical physics never imagined. Others argue observation doesn't require a conscious being. Any interaction that leaves a mark on the environment could count. But Wheeler's vision goes further, proposing that the universe's entire history might be shaped retroactively by what's observed now. In his delayed choice experiments, photons seem to decide their past behavior based on present measurements, as if time itself is flexible under quantum rules. Now stretch that logic back to the dawn of everything. If observation defines reality, then the first quantum superposition might not have fully resolved until life emerged billions of years later, creating a kind of cosmic echo where the universe's birth and our existence are fundamentally linked. It's a poetic thought that stars, planets, and eventually eyes had to form before the cosmos could truly say, "I exist." This blurs the line between creator and creation, suggesting we're not just inhabitants of the universe, we're participants in its very definition, threads in a tapestry still being woven by observation. And that raises an eerie question. If a tree falls in a quantum forest with no one to hear it, does it make a sound? Or does it remain suspended in an eternal maybe, waiting for some future observer to give it meaning, or erase it entirely? Wheeler's universe is alive with potential, a cosmic story still being written by every glance, every measurement, every conscious thought that pins reality into place, one quantum decision at a time. The Boltzmann Brain paradox throws everything we think we know about reality into question with one unsettling possibility. What if you, me, and everything we perceive aren't part of a vast, ancient universe, but momentary glitches in an infinite void? This mind-bending idea comes straight from statistical mechanics, where physicist Ludwig Boltzmann suggested that in an eternal cosmos, random fluctuations could spontaneously create self-aware entities' brains complete with false memories of an entire universe. And if that sounds absurd, the real shocker is how stubbornly this theory resists being dismissed. Here's how it works. In a truly infinite and chaotic universe, even the most improbable events must happen eventually. Given enough time, particles jostling in the void could, purely by chance, arrange themselves into a conscious mind, a Boltzmann brain, complete with fabricated sensory input convincing it of a reality that doesn't exist. Now apply that to quantum origins. If the universe began in a superposition, one fleeting configuration might have birthed not a cosmos, but a single, self-deluded observer. The galaxies, the stars, your childhood memories, all could be an elaborate hallucination lasting just long enough for you to question your own existence before dissolving back into the quantum foam. The implications are staggering. If Boltzmann brains are statistically more likely than stable universes, since a single brain requires far less energy and organization than an entire cosmos, then the odds suggest we're probably the illusions, not the universe. It's like finding a perfectly sandblasted message on a beach and assuming the wind wrote it rather than a person. But here's where quantum mechanics twists the knife. If the universe's first superposition collapsed randomly, who's to say it didn't collapse into the most probable outcome, a fragile, brief consciousness rather than a 14 billion-year space-time epic? Critics argue this reduces reality to a nihilistic absurdity. Why trust any observation if our instruments and measurements might also be figments? Yet the paradox persists because it exposes a flaw in how we equate probability with truth. Maybe the universe isn't likely, maybe it's gloriously, defiantly unlikely, a cosmic underdog that beat the odds. Or perhaps, as some theorists suggest, the very act of sustained observation of questioning reality shifts the probability away from Boltzmann brains. After all, a hallucination that doubts its own existence is far more complex than one that doesn't. So where does that leave us, teetering on the edge of existential vertigo, certainly? But also with a profound insight. The universe's first quantum flicker might have been a choice between eternal silence and a fleeting, self-aware ripple. That we're here discussing it at all could be the strongest evidence that reality chose the harder, richer path. Not just a brain in the void, but a cosmos brave enough to dream itself into being. What if the quantum superposition that birthed our universe wasn't a random cosmic accident, but lines of code in an unfathomably advanced simulation? This is the spine-tingling premise of the simulation argument, where the strange rules of quantum mechanics start to look less like nature's laws and more like clever programming choices. Picture the universe's first moments not as a primordial fireball, but as a subroutine booting up in a hypercomputer so vast its processors could be the size of galaxies. At the heart of this theory lies Nick Bostrom's infamous trilemma, which presents three unsettling possibilities about reality. Either civilizations like ours almost always go extinct before reaching technological maturity, they lose interest in creating simulations of their ancestors, or we're almost certainly living in one. The logic is chillingly simple. If advanced civilizations ever gain the power to simulate conscious minds, they could run countless virtual universes. Statistically, the number of simulated beings would dwarf real ones, making it absurdly likely we're in the simulation. Now tie that back to quantum origins. Why would a simulation start with a superposition? Because it's efficient. In quantum computing, particles in superposition let you perform multiple calculations simultaneously, a cosmic version of multitasking. The universe's initial quantum blur might have been the simulation's way of testing every possible configuration before committing to one. It's like a video game engine rendering only what the player observes to save processing power. The double-slit experiment, where particles behave differently when watched, starts to feel less like quantum weirdness and more like a clever optimization hack. But here's where it gets wild. If the universe is a simulation, then quantum indeterminacy, the idea that particles don't have definite properties until measured, could be a deliberate design feature. Just as a video game only loads detailed textures when you look at them, maybe reality only renders precise outcomes when observed to conserve resources. Even the speed of light, that ultimate cosmic speed limit, might just be the processor's clock rate, the maximum speed at which the simulation can update information across its virtual space. Critics argue this is modern solipsism dressed up in silicon, but the theory gains eerie traction when you consider glitches. The Planck length, the smallest possible unit of space, could be pixelation in the simulation's resolution. Quantum entanglement, where particles instantly influence each other across distances, might be a shortcut in the code, two variables sharing the same memory address. Even dark energy, that mysterious force accelerating the universe's expansion, could be a garbage collection process, freeing up memory by deleting unused sectors of spacetime. Yet the simulation hypothesis isn't just sci-fi nihilism. It reframes existential questions in startling ways. If our universe is programmed, then the architects might have embedded Easter eggs, mathematical constants too perfect to be random, or quantum anomalies that hint at the code beneath. Some physicists even suggest we could test the theory by looking for computational limits in nature, like rounding errors in the fabric of reality. After all, no simulation is perfect. But here's the ultimate twist. If we're in a simulation, then the creators might be too. Simulations could nest inside simulations like Russian dolls, each layer unaware of the next. The universe's first quantum flicker wouldn't be the beginning, just the latest reboot in an infinite stack of realities. each one wondering if it's the original, each one holding its breath as the quantum dice tumble again. Forget the Big Bang. What if our universe was born not from an explosion, but from a cosmic car crash in higher dimensions? The ekpyrotic universe theory paints a picture where reality as we know it began when two vast parallel membranes called branes for short slammed together in a hidden dimension beyond our perception. Imagine two enormous sheets of paper floating in a dark room, drifting closer until they touch, unleashing an unimaginable burst of energy. Now replace those sheets with 11-dimensional structures, each one a universe in its own right, and you've got the recipe for an entirely different kind of creation story. This idea flips the standard Big Bang narrative on its head. Instead of a singularity where space and time explode into existence, the ekpyrotic model suggests our universe emerged from a collision so violent it imprinted quantum uncertainty into the very fabric of reality. According to string theory, these branes could be floating in a higher dimensional bulk space, oscillating back and forth over eons. When they finally collide, the energy released doesn't come from some mysterious point. It's spread evenly across the entire surface of the brain, solving one of the Big Bang's biggest puzzles: why the early universe was so uniform. The cosmic microwave background, that faint afterglow of creation, isn't the echo of an explosion, it's the fingerprint of a universe-wide shiver from the impact. What's truly radical about this theory is how it handles the first quantum superposition. In the moments before collision, the branes exist in a strange quantum state, neither fully separate nor fully merged. The universe to be hangs in limbo, a blur of potential outcomes, until a collision forces one configuration into reality. It's as if the cosmos had to choose its fate at the moment of impact, locking in the laws of physics we now take for granted. This could explain why certain constants, like the strength of gravity or the mass of electrons, have the precise values they do. They're frozen accidents from how the branes happen to collide. But here's where things get even weirder. If the ekpyrotic model is correct, there might be countless other collisions happening right now in higher dimensions, each one birthing a new universe with different rules. Some might have stronger nuclear forces, making stars burn out in seconds. Others could have extra spatial dimensions we can't perceive, where gravity behaves in bizarre ways. And just like ripples in a pond, these collisions might not be one-time events. The branes could keep bouncing apart and crashing together in an endless cycle, meaning our universe might have had countless predecessors, each one resetting the cosmic clock with a new quantum roll of the dice. The implications stretch beyond mere cosmology. If the ekpyrotic universe is real, then dark energy, that mysterious force accelerating the universe's expansion, might actually be the slow recoil of the branes after their collision, pulling space apart as they separate. Even the arrow of time could be tied to the brane's motion, with entropy increasing as they drift farther apart. It's a humbling thought that everything from the formation of galaxies to the heat death of the universe might just be side effects of a higher dimensional dance we'll never see. Yet for all its elegance, this theory leaves us with a chilling question. If our universe is just one sheet in an infinite stack of colliding branes, what or who is moving them? Are these cosmic crashes truly random, or is there some deeper pattern, some hidden physics in the bulk space that choreographs the collisions? The answer might lie in the quantum fuzziness of those first moments, where the universe wasn't just born, it was chosen from an infinite lineup of possibilities, all trembling in the dark before the branes touched and reality clicked into place. What if consciousness isn't just a product of the universe, but a fundamental part of its creation? The Penrose-Hameroff theory of orchestrated objective reduction takes the quantum weirdness of the early cosmos and ties it directly to the inner workings of the mind. At its core, this bold idea suggests that the first quantum superposition wasn't just a random cosmic event. It was a proto-conscious moment, a flicker of awareness woven into the fabric of reality itself. To grasp this, we need to zoom in way in. to the microscopic scaffolding inside our own brains. Microtubules, tiny protein structures in neurons, aren't just cellular scaffolding. According to physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, these structures might be quantum computers vibrating at frequencies that allow them to exist in superpositions until they reach a threshold and collapse into definite states. This collapse isn't random, though. It's orchestrated, guided by the geometry of spacetime itself in a process called objective reduction. And here's the cosmic twist. If this process happens in our brains today, could it have happened on a universal scale at the dawn of time? Imagine the universe in its first fleeting instance, a seething quantum foam where space and time hadn't yet settled into their familiar forms. In this primordial haze, spacetime itself might have vibrated like a cosmic version of brain microtubules, holding countless possibilities in superposition. Then, in a moment of self-awareness as profound as it was fleeting, the universe chose a state, not randomly but through a proto-conscious decision. It's as if reality woke up just long enough to define itself before slipping back into unconscious machinery. This theory bridges two of science's greatest mysteries, the nature of consciousness and the origin of the universe. It suggests that the mind isn't an accidental byproduct of physics, but something woven into reality's deepest layers. The same quantum processes that allow us to think and feel might have been present at the Big Bang, meaning the universe didn't just create consciousness, it remembered it. The implications are staggering. If true, then every thought we've ever had, every moment of awareness, echoes that first cosmic ripple of self-collapse. Critics argue this borders on panpsychism, the idea that consciousness is universal, but Penrose and Hameroff offer a startling counter. Quantum vibrations in microtubules are too delicate to survive in the warm, wet environment of the brain unless they're shielded somehow. Their solution, the universe's first superposition, might have been similarly fragile, needing a kind of cosmic insulation to prevent decoherence, like the strange, near-perfect cold of the early cosmos. And that raises a haunting possibility. If consciousness truly played a role in the universe's birth, then observers like us aren't just passive witnesses. We're inheritors of a quantum legacy, carrying forward that original act of self-definition every time we think, measure, or observe. The universe's first thought might still be unfolding, not in the void, but in the electrical storms of billions of living brains, each one a tiny echo of the cosmic mind that whispered reality into being. Black holes aren't just cosmic vacuum cleaners, they might be cosmic mothers. The black hole genesis theory flips our understanding of creation upside down by suggesting our entire universe wasn't born from nothing, but from the death throes of a collapsing star in another reality. Picture this: a supermassive black hole in some distant cosmos reaches the end of its life, its singularity stretching spacetime to breaking point until pop, it births an entirely new reality inside itself. What we call the Big Bang wasn't the beginning of everything, but the moment a dying black hole's heart ripped open, spilling out a fresh universe like a cosmic Russian nesting doll. At the center of this idea lies the singularity, that infinitely dense point where the laws of physics break down. In our universe, singularities hide behind event horizons, but what if one escaped? Some physicists argue that when a black hole collapses under its own gravity, the singularity doesn't just vanish. It undergoes a quantum phase transition, flipping inside out to become the seed of a new spacetime. Think of it like a balloon being squeezed until it suddenly inverts, its inner surface becoming the outer shell of a new balloon, that moment of inversion. That's the universe's first quantum superposition, a fleeting instant where reality could have become anything before settling into the laws we know today. This theory beautifully solves two cosmic mysteries at once. First, it explains why our universe seems finely tuned for life. If every black hole births a new cosmos with slightly tweaked physics, then we naturally find ourselves in one of the rare universes where conditions allow galaxies and observers to exist. Second, it accounts for the eerie uniformity of the cosmic microwave background. The violent stretching of spacetime during black hole formation would have ironed out irregularities, just like smoothing wrinkles by pulling on a sheet. Even dark energy, that mysterious force accelerating the universe's expansion, might simply be the residual energy of that primordial black hole's death kick. But here's the real kicker. If black holes create universes, then our own cosmos might be studded with embryonic realities. Every time a star collapses into a black hole in our universe, it could be planting the seed for an entirely new cosmos with its own laws of physics. We might be living inside a black hole from an ancestor universe while simultaneously nurturing countless offspring universes in our own black holes, a fractal multiverse where every gravitational monster is a potential Big Bang waiting to happen. The implications ripple outward in dizzying ways. If this theory holds, then the quantum superposition at our universe's birth wasn't just random chance, it was an inheritance. The singularity's final quantum states, shaped by the physics of its parent universe, set the rules for our reality. Some versions of the theory even suggest information can leak between universes through black hole umbilical cords, meaning the constants of nature we measure might be echoes of a cosmos long gone. Yet for all its elegance, this idea leaves us with a haunting question. If our universe was born from a black hole, what or who created the first one? Is there an original cosmos at the top of this infinite family tree? Or does the chain loop back on itself in some paradoxical ouroboros of creation? The answer might lie in the quantum blur of that first superposition, where time itself loses meaning and every beginning could just be another universe's end. What if the universe's first quantum flip wasn't just a random event but a decision made with perfect hindsight? The time-symmetric universe theory throws causality out the window, suggesting the past can be shaped by the future as easily as the future is shaped by the past. Imagine tossing a coin, and instead of it landing randomly, its outcome is somehow nudged by events that haven't happened yet. Now scale that up to cosmic proportions, where the universe's initial superposition wasn't a blind roll of the dice, but a choice informed by everything that would ever come after, including you watching this video right now. This isn't just wild speculation. Quantum retrocausality experiments have already hinted that particles might respond to future measurements in ways that defy linear time. In one groundbreaking study, physicists delayed the choice of how to measure a photon until after it had already passed through a filter, yet the photon's behavior seemed to anticipate that future decision. It's as if reality is a conversation where cause and effect talk in both directions, bargaining over what history makes the most sense. Apply this to the Big Bang, and suddenly the universe's first moments look less like a spontaneous explosion and more like a carefully negotiated agreement between past and future. The implications rewrite cosmic history. If retrocausality is real, then the delicate balance of physical constants, the precise strength of gravity, the exact mass of an electron might not be lucky accidents. They could be the result of a feedback loop spanning billions of years, where the universe's future conditions reached back to fine-tune its birth. Picture a sculptor chiseling a statue, except the sculpture itself guides the artist's hands from the future, ensuring every detail aligns with what's to come. But here's where it gets truly dizzying. If the first quantum superposition was influenced by future events, then free will takes on a bizarre new dimension. Every choice we make today might ripple backward, subtly adjusting probabilities at the dawn of time to make our existence inevitable. It's a cosmic version of the grandfather paradox, where the universe ensures its own consistency by weaving cause and effect into a seamless loop. Some interpretations even suggest that conscious observers like us play a role in this dance, collapsing quantum possibilities not just in the present, but retroactively across the entire timeline. Yet this theory isn't without its critics. The idea of future events influencing the past feels like magic to many physicists. violating deeply held intuitions about how reality should work. But quantum mechanics has a habit of turning intuition on its head. If retrocausality holds, then the universe's origin story isn't a one-way street. It's a Mobius strip of causality, where the first quantum whisper and the last star's flicker are locked in an eternal dialogue, each defining the other across the expanse of time. And that leaves us with a haunting thought. If the future can shape the past, then the universe might not have a true beginning or end, just an infinite negotiation between what was, what is, and what will be. The Big Bang superposition wasn't the first step in a chain of events, but the midpoint of a conversation we're only now learning to hear. The universe's first moments weren't just a quantum free-for-all, they were a cosmic competition where only the fittest states survived. This is the crux of quantum Darwinism, a theory that reshapes how we think about reality's birth by applying the principles of natural selection to the quantum realm. Picture the early universe as a swirling soup of infinite possibilities, every particle, every force, every law of physics existing in a blur of simultaneous states. Then something extraordinary happened. The environment itself began acting like a judge, amplifying certain quantum states while suppressing others until only the most stable configurations remained. It's as if the cosmos played a game of last one standing, where the rules of classical reality weren't predetermined, they were earned. At the heart of this idea lies decoherence, the process that makes quantum weirdness fade away as systems interact with their surroundings. In everyday terms, think of a droplet of ink falling into a glass of water. At first, you can trace its path precisely, a quantum-like certainty. But within seconds, the ink spreads, blending irreversibly with the water until its original state is lost to randomness. Now imagine that droplet is the entire universe, and the water is space itself. Quantum Darwinism suggests our classical reality emerged because certain quantum states were better at replicating themselves across the environment, leaving more copies in the cosmic ledger, while others faded into obscurity. The laws of physics we take for granted, they're not fundamental truths, but the winners of an ancient selection process. This theory turns the measurement problem on its head. Instead of asking why observation collapses quantum states, quantum Darwinism argues that collapse isn't a sudden event, it's a gradual winnowing where only the most robust states endure. For the universe's first superposition, this means the initial quantum fuzziness didn't vanish because some cosmic observer blinked into existence. It crystallized because certain configurations were more resilient to environmental noise, more likely to imprint themselves on the fabric of spacetime. The speed of light, the charge of an electron, even the direction of time's arrow could all be artifacts of this primordial selection, frozen into place as the quantum storm settled. But here's where it gets wild. If quantum Darwinism shaped reality's birth, then other universes might exist where different states won, leading to entirely different physics. Some could have stronger nuclear forces, making stars burn out in seconds. Others might lack stable atoms altogether, existing as formless quantum soups. Our universe isn't special because it was designed, it's special because it survived. This echoes the anthropic principle, but with a twist. The fine-tuning of physical constants isn't luck. It's the inevitable outcome of a cosmic trial by fire where only observer-friendly universes persist long enough to be noticed. Critics argue this borders on circular reasoning. Doesn't the environment itself emerge from quantum states? Yet proponents counter that the selection process is self-reinforcing. The early universe's extreme conditions acted like a filter, privileging states that could scale up to macroscopic stability. It's why we don't see quantum superpositions in daily life. Those fragile states were weeded out billions of years ago, leaving only the robust, classical building blocks we now call reality. Even the act of measurement might not create definite outcomes. It simply reveals which states were already dominant, like an archaeologist brushing sand off a fossil that's been there all along. So what does this mean for the Big Bang's first quantum flicker? That moment wasn't just uncertainty resolving, it was a cosmic democracy in action, with countless quantum states campaigning for existence. The universe we inhabit is the platform that gathered the most votes from its environment, a consensus reality etched into space-time by relentless natural selection. And somewhere, in the static of the cosmic microwave background, there might still be whispers of the loser's ghostly alternatives that almost were, fading like echoes of a dream the universe chose to forget. The universe's birth might not have happened in the dimensions we experience, but on a distant, invisible boundary where reality is written in pure information. The AD-S/CFT correspondence, a radical idea born from string theory, suggests that our entire cosmos could be a holographic projection from a lower dimensional realm where quantum mechanics and gravity finally shake hands. Imagine a shadow puppet show, except the puppets are us, and the screen is the fabric of spacetime itself, while the true story plays out on a wall we can't see, in a language we're only beginning to decipher. At its core, this theory proposes an audacious trade-off: a universe with gravity like ours unfolding in an anti-de Sitter space, a strange, negatively curved geometry, is mathematically equivalent to a quantum field theory living on its boundary where gravity doesn't exist. It's as if the 3D world we know is just a rendering of data stored on a 2D surface at the edge of everything. Apply this to the Big Bang, and suddenly the universe's first quantum superposition takes on a surreal new meaning. That initial moment of uncertainty wasn't confined to a point in space, it was a fluctuation in the cosmic code, a glitch or perhaps an intentional calculation unfolding on the boundary where reality is programmed. What makes this idea so compelling is how it solves physics' greatest dilemma, uniting quantum mechanics with Einstein's theory of gravity. In the boundary theory, the CFT side, particles interact without gravity following clean quantum rules. In the bulk, our universe, spacetime bends and warps under gravity's influence. The AD-S/CFT bridge says these aren't two separate worlds, they're dual descriptions of the same thing. The chaos of a black hole's interior could be perfectly mirrored by orderly quantum interactions on its event horizon, like a fiendishly complex equation balancing both sides of reality. Now stretch this back to the universe's inception. If the AD-S/CFT duality holds, then the Big Bang might not have been an explosion in space, but a quantum computation on the boundary, a single operation in a cosmic processor that rendered our 3D universe as its output. The superposition we've been chasing wasn't a physical state, but a simultaneous processing of every possible universe configuration until one solution prevailed. Think of it like a quantum computer running every possible simulation at once, then projecting the winning version into existence as spacetime. The implications rewrite the rules of existence. If the universe is holographic, then concepts like distance and time might be emergent illusions, convenient fictions our brains cobble together from deeper, stranger data. Even more mind-bending, the boundary where reality is encoded could be timeless, meaning the universe's birth and heat-death might already be written there as static lines of code. We're not living through history, we're watching it play back from an immutable cosmic hard drive. Yet for all its mathematical elegance, this theory leaves us with haunting questions. If we're projections, who or what is running the simulation? Are the laws of physics just default settings in some unfathomable software? And if the boundary holds the truth, will we ever find a way to read our own source code? Some theorists suggest the answer might be written in the universe's oldest light, subtle patterns in the cosmic microwave background that could be signatures of the boundary's quantum operations. Others think black holes are our best clues, their event horizons acting like cosmic USB ports where the hologram interfaces with its projector. One thing's certain, if the AD-S/CFT correspondence describes reality's true nature, then the quantum superposition at creation wasn't just a moment. It was the first frame in a holographic movie we're all still acting in, unaware the script was written long ago on a wall at the edge of the universe. What if the universe needed a mind to bring it into being? The von Neumann-Wigner interpretation pushes quantum mechanics into uncharted territory by proposing a radical idea. Consciousness isn't just a bystander in the quantum world, but the very force that shapes reality. At the heart of this theory lies a startling reversal of conventional physics. Instead of particles existing in definite states that we passively observe, the act of observation itself, the spark of awareness, might be what forces quantum possibilities to snap into concrete existence. Apply this to the Big Bang, and suddenly the universe's first quantum superposition wasn't resolved by random chance, but by the arrival of a primordial observer. This idea traces back to two towering figures in quantum theory, John von Neumann and Eugene Wigner, who wrestled with the infamous measurement problem. In traditional quantum mechanics, particles exist in superpositions until measured, but the theory never explains what actually counts as a measurement. Is it the physicist's notebook, the detector's click, or something deeper? Von Neumann argued the chain of measurement couldn't stop until it reached an irreducible in-point consciousness itself. Wigner took it further, suggesting that even the mathematics of quantum waves collapsing pointed to mind as the ultimate arbiter of reality. Now stretch that logic back to the dawn of time. If consciousness collapses quantum states today, why couldn't it have done so at the universe's birth? The initial quantum fuzziness, where all possible configurations coexisted, might have hung in limbo until the first glimmer of awareness emerged to choose one. This isn't about human minds influencing the past, but about consciousness as a fundamental feature of reality, woven into the fabric of existence from the very first moment. Some versions of the theory even suggest the universe's laws were selected because they allowed observers to eventually arise, a cosmic bootstrap where the end goal, conscious life, retroactively shaped the beginning. Critics dismiss this as quantum mysticism, but the math holds unsettling hints. In the delayed choice quantum eraser experiment, particles seem to decide their past behavior based on future observations, as if time itself bends to accommodate conscious measurement. If quantum systems can be influenced by observers in the present, why not at the moment of creation? It's a dizzying loop where the universe creates observers who then define the universe, like a snake eating its own tail across billions of years. Yet the von Neumann-Wigner interpretation forces us to confront a haunting possibility. If consciousness collapses quantum states, then the universe didn't just happen, it was witnessed into being. The cosmic microwave background, the distribution of galaxies, even the arrow of time might all be artifacts of that first act of observation, frozen into the fabric of reality like footprints in primordial quantum sand. And that raises a question far stranger than any sci-fi. If a universe falls in the void and no one is there to perceive it, does it make a sound? Or does it remain suspended in endless possibility, waiting for a mind to give it form? Imagine the fabric of space and time not as a smooth, unbroken sheet, but as a vast cosmic network, a constantly shifting web of quantum connections where every intersection vibrates with possibility. This is the radical vision of quantum gravity theory, which suggests that spacetime didn't start as the seamless continuum we experience today, but as a frenzy of entangled nodes flickering between infinite configurations. At the universe's birth, this dynamic graph wasn't frozen into rigid geometry. It existed in a roiling superposition, a storm of potential pathways where distance, direction, and even causality had yet to take definite form. The theory gets its name from a clever play on words, graphity blending graph with gravity, and it reimagines reality's foundation in a startling way. Picture billions of microscopic points like dots on an unimaginably complex connect the dots puzzle. In the beginning, these points didn't have fixed relationships. Some were linked, others isolated, and the entire structure fluctuated wildly, exploring every possible arrangement. This wasn't just randomness, it was a quantum democracy where every configuration had its say until, through some cosmic threshold, the graph cooled into stability. The links that survived became the spacetime we know, while the others faded into oblivion, leaving behind only faint echoes in the form of dark energy or quantum foam. What's revolutionary here is how quantum gravity handles the universe's first superposition. Unlike theories where spacetime emerges from strings or branes, this model proposes that geometry itself was undecided, a shimmering haze of maybe where even the number of dimensions hung in the balance. Some nodes might have briefly formed 4-dimensional clusters, others 7-dimensional ones, until the most stable pattern, our familiar 3 spatial dimensions plus time, won out. It's as if the cosmos was a kaleidoscope twisting through every conceivable shape before settling into the one that allowed matter, and eventually life, to exist. But the real magic lies in how this graph evolves. Just as ice crystals form when water cools, spacetime's structure might have frozen from the chaotic quantum connections of the early universe. The links between nodes didn't just define distance, they birthed the laws of physics themselves. Strongly connected clusters could correspond to regions where gravity emerges, while sparse areas might explain cosmic voids or even dark matter's elusive presence. Even the speed of light, that ultimate cosmic speed limit, could simply reflect how quickly information hops between nodes in the graph, like a cosmic game of telephone where the message is reality itself. Critics argue the theory is more math than testable physics, but tantalizing clues hint at its validity. If spacetime is granular at the smallest scales, then ultra-high-energy cosmic rays might reveal slight deviations in their travel, hinting at the graph's underlying lattice. Others suggest the cosmic microwave background could bear faint imprints of the graph's early fluctuations, like wrinkles in a blanket stretched thin by time. Even more intriguingly, quantum gravity might explain why time flows in one direction. The graph's links could have a natural asymmetry, like arrows on a map, guiding the universe's expansion while leaving the past behind. Yet the most profound implication isn't about the past, it's about the future. If spacetime is a dynamic graph, then it might still be changing. Black holes could be regions where the graph reconfigures itself, knots in the cosmic net where connections rewrite the rules. Wormholes, if they exist, might be shortcuts through the graph's hidden architecture, tunnels stitched between distant nodes, and dark energy's mysterious push. Perhaps the graph is still evolving, adding new links in the void, stretching the universe from within like a living thing growing its own skeleton. Quantum gravity doesn't just redefine the universe's first moment, it turns reality into a cosmic conversation, where every particle, every force, is just another voice in an endless negotiation between connection and chaos. The superposition we've been chasing wasn't a fleeting accident, it was the universe's first and greatest debate, a vote among infinite possibilities that set the stage for everything to come. And somewhere in the quiet hum of empty space, those quantum whispers might still be going on. What if the Big Bang wasn't the beginning, just the latest reboot in an endless cosmic cycle where universes rise, fall, and are reborn from their own ashes? This is the breathtaking vision of conformal cyclic cosmology, or CCC, a theory pioneered by Nobel laureate Roger Penrose that reshapes our understanding of time itself. In this radical framework, the universe's first quantum superposition wasn't a one-time event, it was the latest iteration of an eternal rhythm, where the death of one cosmos becomes the cradle for the next in an infinite loop of creation. At the heart of CCC lies a strange symmetry, not of space but of scale. When our universe reaches its heat death, all matter will eventually decay into massless particles like photons, leaving nothing but an ocean of pure energy stretching endlessly into the future. But here's the twist to these particles: a universe devoid of structure has no meaningful scale. A single photon in this frozen wasteland experiences time and distance completely differently than we do. From its perspective, the vast, empty cosmos becomes mathematically identical to the hot, dense singularity of a new Big Bang. In this way, the far future of one universe seamlessly becomes the beginning of another, connected by a transformation Penrose calls conformal rescaling, a cosmic reset button hidden in the equations of general relativity. This is where black holes play their most astonishing role. According to CCC, these gravitational monsters aren't just stellar graveyards, they're time capsules preserving quantum information from one eon to the next. As black holes evaporate over eons via Hawking radiation, they imprint faint patterns onto the fabric of spacetime. These imprints, known as Hawking points, might still be visible in our universe's cosmic microwave background, ghostly signatures from the cosmos that came before us. Imagine finding hieroglyphics etched into the afterglow of creation, messages from a universe long dead, carried across the void by the last whispers of its black holes. The implications for quantum superposition are staggering. If CCC is correct, then the universe's initial blur of possibilities wasn't random chance, it was an inheritance. The quantum states that collapsed to form our cosmos were shaped by information bleeding through from previous eons, like a cosmic game of telephone spanning eternity. This could explain why fundamental constants seem so finely tuned for life, not because of divine intervention, but because each cycle subtly selects for configurations that allow complexity to arise. The laws of physics aren't fixed, they're learned behaviors refined across countless iterations of cosmic dawn and twilight. Yet the true brilliance of CCC lies in how it solves one of physics' greatest puzzles, the low entropy state of the early universe. Why did the Big Bang start with such perfect order? Penrose's answer: because it wasn't truly the beginning. That pristine order was the gift of countless black holes from the prior eon, their monstrous appetites having effectively reset entropy's clock by swallowing chaos and leaving behind clean slate. In this view, our universe's first quantum flicker wasn't pure uncertainty. It was a carefully prepared canvas, its probabilities weighted by the accumulated wisdom of cycles beyond counting. Critics argue CCC stretches cosmology to its breaking point, but Penrose and his collaborators have found tantalizing evidence. Strange, circular patterns in the cosmic microwave background, dubbed Hawking points, could be the thermal shadows of primordial black holes from a previous eon. If confirmed, these faint rings would be the first concrete evidence we're living in just one chapter of an infinite cosmic saga. Even more provocatively, CCC suggests time itself might be an illusion, a local phenomenon that dissolves at the boundary between eons, where the universe forgets its past to begin anew. So where does that leave us? Not at the start of time, but in the middle of an endless dance where universes breathe in and out like some unimaginable lung. The quantum superposition we've been chasing wasn't the first, and if CCC is right, it won't be the last. Somewhere in the unimaginable future, the last black hole of our cosmos will exhale its final photon, and in that moment, another quantum dice will roll, another universe will gasp its first breath, and the cycle will begin again. Not with a bang, not with a whimper, but with the quiet certainty of a cosmic heartbeat that never truly stops. Einstein's famous equations might have been whispering the universe's deepest secret, all along hidden in the ghostly link between wormholes and quantum entanglement. The ER equals EPR conjecture, a theory as elegant as it is revolutionary, suggests that the universe's first quantum superposition wasn't just a blur of possibilities, but a cosmic bridge stitching reality together from the inside out. Picture this: two particles entangled across the cosmos, their fates intertwined no matter the distance, and the fragile thread connecting them isn't some abstract force, but a microscopic wormhole woven into spacetime itself. What if the Big Bang wasn't a single point exploding outward, but a quantum handshake between two realms with spacetime as the handshake's echo? At the heart of this idea lies a stunning unification. Stands for Einstein-Rosen, bridges the formal name for wormholes, while EPA honors Einstein, Podolsky, and Rosen, who first grappled with quantum entanglement's spooky action at a distance. For decades, these concepts lived in separate worlds, wormholes as spacetime shortcuts in general relativity, entanglement as quantum weirdness defying classical physics. But then came Juan Maldacena and Leonard Suskind's bold proposal. What if they're two sides of the same coin? Imagine a pair of entangled particles not just mysteriously linked, but physically connected by a wormhole too tiny to see, a thread of warped spacetime binding them. Now scale that back to the universe's birth, and suddenly the first quantum superposition transforms from a hazy maybe into a cosmic umbilical cord, a quantum wormhole threading through the newborn cosmos, tying its parts together before space and time even settled into place. This isn't just poetic imagery, it's math with teeth. If ER equals EPR holds, then the early universe's quantum fuzziness wasn't randomness, but a network of microscopic wormholes, each one a tunnel through which information could flow. The Big Bang's famous uniformity, why opposite sides of the cosmos look so similar despite never having been in contact, might not require faster than light inflation. Instead, those regions were always connected, not by expanding space, but by a web of primordial wormholes like veins in a cosmic body. Even black holes, those infamous information destroyers, might just be wormholes in disguise, their entangled particles holding the key to unlocking the universe's first stitches. But the real magic happens when you consider what this means for superposition. In standard quantum mechanics, a particle in superposition exists in multiple states until measured, but no one knows how. AR equals EPR offers a breathtakingly concrete answer. The particle isn't just mathematically undecided, it's physically torn, with each possible state connected by a wormhole too small to see. The moment of measurement isn't some abstract collapse, it's the wormhole snapping shut, forcing the particle to choose one end of the tunnel. Apply this to the universe's first moments, and suddenly that initial quantum blur isn't a featureless fog, it's a labyrinth of wormholes, each one a thread in spacetime's loom, weaving reality into existence one connection at a time. Critics argue that these wormholes would be too unstable to matter, evaporating in flashes of Hawking radiation. Yet supporters counter that quantum entanglement's resilience, particles staying linked even when separated by galaxies, hints at something deeper. If entanglement is wormholes, then the universe's very fabric might be held together by these quantum stitches, invisible threads keeping everything from flying apart. Even dark energy's mysterious push could be the tension of these microscopic bridges stretching as the cosmos expands, like rubber bands straining against infinity. And here's where it gets truly cosmic. If ER equals EPR is right, then the universe's first superposition wasn't a solitary event. It was the first note in a symphony of entanglement, a song spacetime never stopped singing. Every particle, every star, every conscious thought might still be riding the echoes of those primordial wormholes, their quantum whispers woven into the atoms of our bodies and the light of distant quasars. The boundary between past and future, here and there, even is and isn't, might not be walls at all, just tunnels we haven't learned to see. And somewhere in the quiet hum of empty space, those first quantum bridges might still be vibrating, waiting for us to listen. What if time isn't a fundamental feature of reality, but an illusion born from heat? The thermal time hypothesis flips our understanding of the universe's first moments upside down by suggesting time itself, and even the quantum superposition that birthed reality, emerged from something far simpler, the flow of energy from hot to cold. Picture a cup of coffee left on a counter. As heat gradually seeps into the air, time seems to pass. But what if that temperature difference isn't just marking time, but creating it? Now scale that up to cosmic proportions, where the entire universe's history might just be thermodynamics in disguise. At the heart of this radical idea is a simple but profound observation. Every measurement of time we've ever made relies on some form of energy transfer. Atomic clocks tick because electrons jump between energy levels. Pendulums swing as potential becomes kinetic. Even our biological sense of time depends on chemical reactions shuffling heat around. Strip away these processes and the concept of time loses all meaning. The thermal time hypothesis takes this a step further, proposing that time isn't an independent dimension at all. It's a side effect of quantum systems seeking equilibrium, a cosmic mirage born from the universe's relentless drive toward maximum entropy. Apply this to the Big Bang's quantum superposition, and suddenly the first moments of existence take on a startling new light. That initial blur of possibilities where every potential configuration of the universe coexisted wasn't hovering in some abstract temporal void. It was a thermodynamic Wild West where quantum fluctuations created microscopic pockets of order and chaos, hot and cold. As these gradients evened out, they didn't just produce heat, they generated the illusion of time's arrow, with the universe's first choices, which quantum states would collapse into reality, being driven by the statistical need to maximize entropy. It's as if reality bootstrapped itself into being by playing a game of thermodynamic pinball, with time emerging as the scorekeeper for energy exchanges between quantum states. This reshapes how we think about the arrow of time. In classical physics, time's one-way flow is a mystery. Why do eggs splatter but never unsplatter? The thermal time hypothesis offers an elegant answer, because entropy increase isn't happening in time, it is time. The universe's first quantum superposition was like a deck of cards shuffled into perfect disorder, not because some cosmic hand dealt them that way, but because thermodynamics demanded it. Those early moments weren't a countdown to reality. They were the first stirrings of a heat engine vast enough to birth time itself. But here's where it gets truly mind-bending. If time emerges from thermodynamics, then the universe's initial quantum fuzziness might still be with us, just hidden in plain sight. At the quantum scale, particles constantly exchange energy, creating fleeting thermal gradients that could be tiny fragments of time being born and dying. Some theorists even suggest black holes are where this illusion breaks down, their immense gravity creating such extreme thermodynamics that time distorts or even stops at their event horizons, like a broken heat engine freezing the clock. Critics argue this reduces time to a mere accounting trick, but proponents counter that it solves one of physics' deepest puzzles. Why quantum mechanics time-symmetric and thermodynamics time-asymmetric seem to disagree about time's nature? The answer: they're two sides of the same coin. Quantum systems create the thermal gradients that birth time, making the universe's first superposition not just a quantum event, but the first tick of a cosmic metronome set by entropy's beat. So where does that leave us? Not in a universe unfolding along some pre-existing timeline, but in a vast heat engine where every energy exchange, from the spin of electrons to the fusion of stars, is quietly weaving the fabric of time itself. The superposition we've been chasing wasn't frozen in some abstract past. It's still happening in the warmth of your skin, the glow of your screen, the hum of distant galaxies, all resonating with the echo of that first thermodynamic whisper that taught reality how to move forward. There's a radical twist to quantum mechanics that doesn't just challenge our understanding of reality, it redefines what probability even means. Quantum Bayesianism, or cubism, flips the script on the universe's first superposition by arguing those shimmering probabilities weren't properties of the cosmos itself, but reflections of the observer's uncertainty. Imagine rolling a die hidden under a cup. Until you lift it, the outcome isn't just unknown, it's fundamentally undefined. Cubism applies that logic to quantum origins, suggesting the Big Bang's quantum blur wasn't an objective state of the universe, but a cosmic expression of ignorance. At its core, cubism treats quantum probabilities as personal bets, Bayesian degrees of belief about future experiences. When a physicist says an electron has a 50% chance of spinning up or down, they're not describing some inherent property of the electron. They're expressing how confident they feel about what they'll measure next. Scale this up to the universe's birth, and suddenly that initial superposition transforms from a physical reality into a kind of cosmic placeholder, a mathematical shrug acknowledging that without an observer, questions about how things really were might not even make sense. This resonates eerily with the mysteries of quantum foundations. Why does observation collapse wave functions? Cubism's answer: because quantum mechanics isn't about the world out there. It's a tool for navigating uncertainty within our own experience. The universe's first quantum jitter wasn't resolved by some disembodied cosmic observer, but by the inevitable interactions that carved reality into shareable facts. It's as if the cosmos bootstrapped itself into definiteness not through external measurement, but through the sheer necessity of creating a consistent history, one that would later include observers like us looking back and wondering how it all began. Critics dismiss this as solipsism in scientific clothing, but cubists counter with a provocative thought experiment. Imagine two alien civilizations evolving on opposite sides of the universe, each developing quantum theory independently. Would their probability assignments match? Not necessarily, because probabilities are shaped by local experiences. Apply that to cosmology, and the Big Bang's probabilities might not have been universal truths, but context-dependent best guesses encoded in the universe's early quantum state. The cosmic microwave background's patterns, less a snapshot of objective reality, more like a fossilized belief structure, a relic of the universe's first educated guess about itself. Where cubism gets truly radical is in its handling of quantum weirdness. Entanglement isn't spooky action at a distance, just two agents updating their beliefs in sync. Schrödinger's cat isn't simultaneously dead and alive. Those terms reflect our preparedness for either outcome. Extend this to cosmic origins, and the universe's first superposition wasn't a simultaneous existence of all possibilities, but a mathematical placeholder for our current ignorance about how existence crystallized from potential to actual. Yet this raises a profound question. If quantum probabilities are subjective, what anchors reality's shared structure? Cubism's sneaky brilliance lies in its answer into subjectivity. While my probabilities and yours might differ initially, the act of comparing notes forces our beliefs to converge. On a cosmic scale, this suggests the universe's apparent consistency, why we all agree on the speed of light or the charge of an electron, emerged from a kind of quantum social contract, where early quantum fluctuations reached consensus through countless interactions. The first superposition didn't collapse, it negotiated itself into stability. The implications ripple through time. If cubism is right, then searching for some pristine, observer-independent quantum beginning might be futile, like trying to hear a tree fall in a forest where sound itself hadn't yet been defined. The universe's birth wasn't witnessed into being, but neither was it indifferent to observation. It existed in that peculiar cubist limbo, not quite real until the story included storytellers, yet not quite imaginary either. A cosmic maybe that became definite not when someone looked, but when the looking became inevitable. This leaves us with a startlingly human vision of quantum origins. One where science doesn't reveal reality's cold, hard truths, but reflects our evolving conversation with a universe that only speaks in probabilities until we ask the right questions. The Big Bang's first quantum whisper wasn't a declaration, but an opening line in a dialogue that's still unfolding, one where every measurement, every observation, is less a discovery and more a continuation of that very first cosmic conversation. The universe's first quantum moment might have been a conversation not just between particles, but between future and past. The transactional interpretation of quantum mechanics paints a surreal picture where reality emerges from waves reaching backward and forward in time, locking together in a cosmic handshake that births existence itself. Imagine throwing a stone into a still pond, but the ripples don't just spread outward, they also travel backward in time, meeting the stone before it even hits the water. Now replace that stone with the Big Bang, and you've got the breathtaking premise of this theory. The universe's initial superposition wasn't a passive state, but an active negotiation across time. At the heart of this idea are two ghostly quantum waves moving in opposite temporal directions. Retarded waves ripple forward in time just as we'd expect, while advanced waves surge backward, carrying influence from future events to the past. Normally, these waves cancel each other out except when they synchronize perfectly, forming what physicists call a handshake. These handshakes are the transactional interpretation's answer to quantum collapse. Reality solidifies when these temporal echoes find resonance, like two singers harmonizing across the ages. Apply this to the universe's birth, and suddenly the initial quantum fuzziness becomes a chorus of potential handshakes, each one a possible reality waiting to be ratified by its own future. What makes this theory so radical is how it redefines causality. In classical physics, causes always precede effects, but here, effects can reach back to shape their causes. Picture a sculptor carving a statue where the finished form somehow guides the chisel strokes that came before. At the cosmic scale, this suggests the universe's first quantum states weren't just random, they were sculpted by the future they would create, a self-fulfilling prophecy written in the language of waves. The cosmic microwave background's intricate patterns, not just frozen relics of the past, but signatures of future galaxies and black holes whispering back to the moment of creation, reinforcing the quantum choices that made their existence possible. This time-symmetric dance could explain one of quantum mechanics' deepest mysteries, why observation collapses superpositions. In the transactional framework, measurement isn't a passive act, it's the culmination of a handshake spanning eons. When a physicist measures an electron's spin, the result isn't random. It's the only outcome consistent with both the particle's past and the detector's future. Now zoom out to the Big Bang, and the universe's first superposition collapses not because of some external observer, but because the cosmic future, every star, planet, and conscious being yet to come, reached back to confirm its existence, like an audience applauding a play into reality. Critics argue this veers into metaphysical fantasy, but the math holds surprising power. The transactional interpretation naturally explains quantum entanglement's spooky connections. Two particles remain linked because their handshakes span space and time, weaving an unbreakable bond. Even the double-slit experiment's bizarre results clarify. Particles behave as waves when future handshakes remain open, but as particles when a specific outcome becomes inevitable. On a cosmological scale, this suggests the universe's expansion, the formation of galaxies, even the emergence of life might all be part of an unimaginably vast handshake, with reality's first quantum flicker still echoing in the way planets orbit and neurons fire. Yet the most haunting implication isn't about physics, it's about time's illusion. If advanced and retarded waves shape reality equally, then the arrow of time might be a statistical fluke, a side effect of more handshakes aligning in one direction. The Big Bang's superposition wasn't the start of time, but the midpoint of an eternal negotiation where what we call the past and future are just two halves of a conversation we're only now learning to hear. And somewhere in the quantum static between stars, those first handshakes might still be resonating, binding every atom in the cosmos to choices made before time had a name. What if the universe's first quantum flicker wasn't a cosmic accident, but the booting up of an unfathomably vast computer? Digital physics dares to imagine reality as a computational process where the Big Bang wasn't an explosion of energy, but the initiation of a cosmic algorithm crunching through its first line of code. In this startling framework, the initial quantum superposition wasn't just uncertainty, it was the universe's processor cycling through potential states like a cosmic version of Hello World. Waiting to execute, Picture the early cosmos not as a seething plasma, but as a grid of discrete cells, each one a bit of cosmic memory capable of storing simple information. These cells wouldn't just sit idly, they'd follow deterministic rules, updating their states based on their neighbors in a rhythmic dance of computation. This is the world of cellular automata, where staggeringly complex behavior emerges from elementary interactions. The game of life, a simple simulation where squares light up or dim based on nearby squares, demonstrates how basic rules can generate intricate, self-sustaining patterns. Now imagine that game played on the scale of the cosmos, with quantum fluctuations as the pixels of a reality-sized display, the universe's first superposition. That was the system loading all possible initial configurations before settling into the one that allowed galaxies, stars, and eventually conscious observers to evolve. The implications rewrite physics at its roots. If the universe is computational, then quantum superposition isn't a mysterious property of matter. It's the natural behavior of information waiting to be processed. Schrödinger's famous cat, neither dead nor alive until observed, becomes a cosmic placeholder, a variable in the universal code holding multiple values until the runtime resolves it. Even entanglement, the eerie link between particles across vast distances, might simply be two variables sharing a memory address in the cosmic RAM, the speed of light. That's the processor's clock rate, the maximum speed at which information can propagate through the grid. But here's where digital physics gets truly radical. If reality runs on computational rules, then the laws of physics aren't fundamental, they're emergent properties of the underlying code. Gravity, electromagnetism, even the passage of time could be high-level phenomena, like the smooth animation on your screen emerging from the rapid refresh of individual pixels. This means the universe's first quantum decision wasn't governed by abstract mathematics, it was a hardware limitation, a trade-off between processing power and the complexity of the simulation. The fact that our cosmos has three spatial dimensions might not be a deep truth, but an optimization choice, a Goldilocks balance between computational expense and the richness needed for life. Critics argue this reduces existence to sterile circuitry, but supporters counter with a profound insight. If the universe is a computation, then it's one that generates its own meaning. The cosmic algorithm didn't just calculate atoms, it computed consciousness, self-reflection, and the ability to question its own nature. Every thought you've ever had might be the universe's way of observing itself, a recursive function in the grand program waking up to its own existence. And that raises an eerie possibility. If our reality is digital, then the initial superposition wasn't a one-time event, it's an ongoing process, with every quantum measurement continuing the cosmic computation. The universe isn't a finished product, it's a live simulation, rendering reality moment by moment as it's observed. Somewhere in the silence between stars, the first line of cosmic code might still be running, an echo of that original quantum ambiguity now woven into every decision, every collision, every spark of awareness that whispers back to the void, still computing. David Bohm saw the universe not as a collection of separate objects, but as an unbroken dance of hidden connections, a cosmic hologram where every part contains the whole. His revolutionary idea, the implicate order, suggests reality as we know it is just the unfolded surface of something far deeper, a quantum realm where past, present, and future coexist in shimmering potential. Imagine dipping a pen into a vat of thick syrup and twisting it slowly. The swirling patterns seem chaotic, but follow rigorous hidden relationships, the syrup's every motion encoding the pen's entire path. For Bohm, the universe works the same way. The Big Bang's first quantum superposition wasn't randomness, it was the initial ripple in this infinite syrup, the first fold in a reality where everything remains secretly connected beneath the surface. At the heart of this theory are hidden variables, not as clumsy fixes to quantum weirdness, but as threads weaving through an implicate fabric we can't directly perceive. While traditional quantum mechanics treats particles as probability clouds, Bohm saw them as guided by a quantum potential, an invisible field carrying information about the entire universe. Picture a surfer riding a wave. The particle is the surfer, but the wave itself is shaped by every other wave in the ocean. In Bohm's cosmology, the universe's first moments weren't a split between possibilities, but a single undivided movement where all outcomes existed enfolded, like the grooves of a vinyl record holding symphonies yet to be played. This reshapes how we view quantum superposition. Schrödinger's cat isn't paradoxically alive and dead. It's simply two states still coiled together in the implicate order, waiting to unfurl. Entanglement's spooky connection. No spook at all, just distant particles responding to the same deeper rhythm, like two leaves twisting in sync on opposite sides of a flowing river. Even the Big Bang's uniformity makes sudden sense. If the early universe was a single quantum potential vibrating in the implicate realm, its smoothness wasn't luck, it was inevitability, a cosmic symmetry preserved because nothing had yet been torn apart. But Bohm's vision goes beyond metaphor. His mathematics describe a pilot wave guiding particles along deterministic paths that only appear probabilistic because we're seeing the unfolded surface of a reality still tangled at its roots. Apply this to cosmology, and the universe's expansion isn't just space stretching. It's the continuous unfolding of hidden relationships, like a flower blooming according to seeds planted in the quantum soil of the implicate order. Dark matter's elusive pull, perhaps the gravitational shadow of folds not yet revealed, while dark energy could be the tension of the cosmic fabric straining to enfold again. Critics argue this trades one mystery for another. What is the implicate order made of? But Bohm's framework offers something radical, a universe where consciousness isn't an accident but woven into the fabric. If observation affects quantum systems, it might be because minds participate in the unfolding, not as outsiders, but as expressions of the same implicate wholeness. The universe's first quantum moment, then, wasn't a solitary event. It was the first note in a symphony still being composed, with every act of observation adding harmonies to the score. And here's the breathtaking implication. If Bohm was right, superposition never truly collapses. Schrödinger's cat, the double-slit experiment's puzzling results, even the cosmic microwave background's fluctuations, they're all surface ripples of a deeper, living unity. The quantum choices we think are random might be echoes of a grander pattern, resonating across dimensions we can't yet measure. Somewhere in the quiet between measurements, the universe might still be whole, just waiting for us to learn how to see the folds. Condensed matter physics, the study of solids and liquids, might seem worlds apart from cosmology, but dig deeper, and you'll find an eerie mirror reflecting the universe's first quantum mysteries. Take topological insulators, materials that defy conventional physics by acting as insulators on the inside while conducting electricity flawlessly on their surfaces. This bizarre behavior arises from quantum entanglement and symmetry, the same fundamental ingredients that might have shaped the universe's earliest moments. Inside these materials, electrons don't just move, they exist in a dance of superposition, their paths impossibly intertwined like cosmic strings vibrating in multiple dimensions at once. What's astonishing is how these materials mimic spacetime's own quantum origins. When cooled to near absolute zero, certain superconductors exhibit emergent gravity, a phenomenon where collective quantum behaviors produce effects indistinguishable from gravitational fields. It's as if the fabric of spacetime itself could emerge from entangled quantum states, just like the universe's first superposition might have birthed gravity as we know it. Theorists even speculate that the cosmic inflation, the universe's explosive early expansion, could resemble a phase transition in these materials, where quantum fluctuations suddenly freeze into a stable configuration, locking in the laws of physics like a crystal forming from a chaotic soup. The parallels grow stranger. In quantum spin liquids, a state of matter where electrons refuse to settle into orderly patterns even at ultra-low temperatures, particles behave as if they're navigating a universe with fractional dimensions. This fractionalization echoes how spacetime might have flickered between dimensional configurations during the Planck epoch, the universe's first incomprehensibly brief moment. Some models suggest that just as defects in these materials can trap exotic quasi-particles entities that act like fractions of an electron, similar cosmic defects in the early universe's quantum field could have seeded galaxies or even dark matter. Here's the radical implication. If exotic materials can simulate quantum gravity in the lab, then the universe's first superposition might not have been a singular event, but an ongoing process, a kind of cosmic condensed matter system where spacetime itself is the emergent phenomenon. The Big Bang's quantum blur could have been less like an explosion and more like a superconductor cooling into a new phase, with the laws of physics crystallizing from a deeper quantum substrate. This shifts the search for quantum gravity from abstract math to something we might one day engineer, manipulate, or even observe in a tabletop experiment. Critics argue these analogies are just mathematical coincidences, but supporters point to startling consistencies. The way entangled electrons in topological materials, remember, their quantum states mirrors how black holes might preserve information on their event horizons. Even the famous holographic principle, the idea that our 3D universe could be encoded on a 2D surface, finds parallels in how 2D sheets of graphene exhibit properties of 3D systems. It's as if the universe left breadcrumbs in the quantum behavior of humble materials, whispering hints about its own origins. Perhaps the most profound takeaway isn't just about physics, it's about perspective. For decades, we've looked to the stars for answers about quantum gravity, but the key might lie closer than we imagined, in the strange quantum dances of electrons here on Earth, echoing the universe's first uncertain steps out of superposition. After all, if a speck of carefully arranged atoms in a lab can mimic the birth of spacetime, then reality might be far more fluid and far more wondrous than we ever dared to dream. The universe might not have been randomly born from quantum chaos. It could have been deliberately chosen by the very existence of those who would one day observe it. This is the spine-tingling premise of anthropic quantum selection, a theory that merges quantum mechanics with the anthropic principle to suggest reality's first superposition didn't collapse by chance, but because conscious observers like us eventually emerged to witness it. Think of it like a cosmic version of the tree falling in the forest, except the tree is the entire universe, and its existence depends on someone being there to hear it. At the heart of this idea lies the anthropic principle, which states that the universe's laws appear finely tuned for life because, well, we're here to notice them. If gravity were slightly stronger or electromagnetism weaker, stars wouldn't form, chemistry would fail, and observers like us wouldn't exist. But anthropic quantum selection takes this a step further. It argues that the universe's initial quantum states weren't just compatible with life, they were selected by the inevitability of life. The moment of creation wasn't a blind dice roll. It was a cosmic filtering process where only observer-friendly configurations survived. Picture the early universe as a labyrinth of branching quantum possibilities. In one path, gravity is too weak to clump matter into galaxies. In another, particles decay too quickly for atoms to form. But in a vanishingly rare subset of paths, the numbers align perfectly. Planets coalesce, molecules dance, and conscious beings eventually gaze back at the cosmos, wondering how they got there. According to this theory, those hospitable paths aren't just lucky outliers, they're the only ones that ever truly solidified into reality. The rest, they evaporated like mirages, collapsing back into the quantum foam the moment it became clear no one would be around to perceive them. This isn't just philosophy, it's math with teeth. In quantum mechanics, the act of observation famously determines outcomes, but the anthropic twist suggests the observers don't have to be present at the beginning. Their inevitable future existence could reach back retroactively like a cosmic safety net, ensuring the universe's first quantum choices lead to a reality where such observers are possible. It's as if the universe bootstrapped itself into being by anticipating its own future, with the initial superposition acting as a placeholder until the conditions for consciousness were guaranteed. Critics argue this borders on circular reasoning. Doesn't the existence of observers require a universe capable of producing them first? Yet proponents counter with a striking analogy. Imagine a deck of cards shuffled until a perfect royal flush appears. Normally, this would take millions of tries, but if every failed shuffle erased itself from history, leaving only the successful one, an outside viewer would see a stacked deck. Similarly, the universe's apparent fine-tuning might just be the illusion left by countless failed quantum branches that never fully materialized, pruned away by the sheer impossibility of sustaining observers. Where this gets truly radical is in its handling of the multiverse. If every possible quantum outcome spawns a separate universe, then anthropic selection suggests we don't inhabit a random branch, we're in the one that inevitably led to us, like a river carving its own canyon over eons. The cosmic microwave background's delicate fluctuations, the precise strength of the nuclear forces, even the arrow of time itself could all be artifacts of this primordial selection bias, with the universe's first quantum flicker acting less like a lottery and more like a cosmic job interview, where only realities that could eventually answer the question, "Why me?" were hired. Yet the most haunting implication isn't about the past, it's about the future. If observers shape reality retroactively, then our continued existence might be quietly reinforcing the universe's fundamental laws right now, like a tree's roots stabilizing the soil it grows in. Every experiment, every telescope's gaze, every conscious thought could be part of an unspoken cosmic covenant, a deal struck at the dawn of time where the universe agreed to exist and we agreed to witness it. And somewhere in the quantum static between galaxies, that first choice might still be whispering not, "I think, therefore I am," but "I am, therefore I was." What if the universe's first quantum superposition never truly ended, but instead repeated itself endlessly, like an echo bouncing between the infinitely large and unimaginably small? The fractal universe hypothesis paints a cosmos where the same patterns of uncertainty and possibility play out at every scale, from the trembling dance of subatomic particles to the sprawling arms of galaxies. Imagine zooming into a snowflake under a microscope, only to find its delicate branches contain entire galaxies, then zooming into one of those galaxies and discovering the same intricate patterns repeating down to the quantum foam. This isn't just poetic symmetry, it's a radical reimagining of reality where the Big Bang's quantum blur wasn't a one-time event but the first note in an infinite cosmic fugue. At the heart of this idea lies fractal geometry, the study of shapes that repeat their structure at smaller and larger scales. Think of a coastline from space. It looks jagged, but zoom in, and the same jaggedness appears in every bay and cliff down to the grains of sand. Apply this to quantum mechanics and suddenly particles behaving as waves aren't just tiny oddities, they're microcosms of the universe's own undecided beginnings. The same superposition that birthed galaxies might still be vibrating in every electron's uncertain spin, every photon's split-path journey. Even black holes, those voracious gravitational pits, could be fractal nodes, their event horizons echoing the boundary of the observable universe in precise mathematical harmony. This theory didn't emerge from pure speculation. Scientists have noticed eerie similarities between the distribution of galaxies in cosmic webs and the branching patterns of neural networks in the human brain. The universe's large-scale structure, with its voids and filaments, mirrors the clustering of quantum fluctuations in the early cosmos, Some mathematicians argue this isn't coincidence but evidence of a deeper fractal order, where the same algorithm generates reality at every level. The cosmic microwave background's temperature variations, they might not be random noise, but the fingerprints of a universe that never stopped being quantum at its core. But the true power of this hypothesis lies in how it demystifies quantum weirdness. If superposition is fractal, then Schrödinger's cat isn't a paradox, it's a scaled-down version of the cosmos' own simultaneous possibilities. Entanglement's spooky connection across space, just the universe's fractal threads vibrating in unison, like spiderwebs trembling at the same frequency no matter how far apart their strands stretch. Even dark matter's elusive presence could be a shadow of this recursiveness, matter existing in superpositions we can't yet detect because our instruments are tuned to only one scale of the fractal melody. Critics argue this borders on numerology, finding patterns where none exist. Yet the math holds startling beauty. Fractal equations reproduce the clustering of galaxies more accurately than traditional models in some simulations. Quantum field theories even hint at scale invariance, where physical laws hold true regardless of magnification, a hallmark of fractal systems. If the universe is truly scale-free, then the quantum rules governing atoms might apply equally to galaxy clusters, with superposition as the bridge between them. The implications rewrite our place in the cosmos. We're not just observers of quantum effects or inhabitants of a classical universe. We're fractal expressions of that first superposition, living in a reality where every decision, every observation, ripples across scales we can't perceive. The stars aren't distant suns, their quantum fluctuations grown vast. The void between them isn't empty, it's pregnant with the same potential that birthed everything, waiting for the next turn of the fractal spiral. And somewhere, in the quiet spaces between your thoughts and the spin of distant quasars, the universe's first quantum whisper might still be repeating itself forever. Neutrinos, those ghostly particles that slip through planets like they're not even there, might have been the universe's first quantum architects. The neutrino oscillation genesis theory proposes that these elusive particles didn't just witness the early cosmos. Their intrinsic instability could have tipped the scales, forcing the universe's first superposition to collapse into the reality we recognize today. Picture a cosmic game of Jenga where every block is a quantum possibility, and neutrinos were the subtle nudge that made the tower finally fall. Here's how it works. Neutrinos come in three flavors: electron, muon, and tau, but they don't stay put. As they travel near light speed, they oscillate between these identities like chameleons cycling through colors. This isn't just a quirky particle trait, it's quantum mechanics in action. Each oscillation represents a superposition, a neutrino existing as all three flavors at once until it interacts with something and picks one. Now rewind to the universe's first picoseconds, when temperatures were so high that neutrinos outnumbered atoms by billions to one. In that seething quantum soup, neutrinos weren't just passive bystanders. Their relentless oscillations could have acted like a cosmic metronome, their rhythmic flavor swaps gradually leaking quantum coherence into the environment. This process, called decoherence, is how quantum weirdness transforms into classical certainty. Imagine a room full of whispering neutrinos, each one's oscillations subtly influencing its neighbors. Over time, these whispers grow into a roar, drowning out the quantum fuzziness until the universe's initial superposition crystallizes into definite states. It's not that neutrinos measured the cosmos into existence. They didn't need to. Their sheer abundance and restless nature made them the perfect medium to bleed quantum ambiguity into the fledgling universe like ink dispersing in water. The implications rewrite our understanding of cosmic dawn. If neutrinos drove decoherence, then the universe's transition from quantum to classical wasn't instantaneous. It unfolded at the speed of neutrino oscillations. The cosmic microwave background's delicate temperature variations might even bear their fingerprints. subtle imprints of how these particles sculpted reality's first structure. Even dark matter's mysteries could tie back to this. Some theories suggest sterile neutrinos, a hypothetical fourth flavor that doesn't interact at all, might be hiding in the shadows of these early oscillations, their quantum silence leaving gaps we now call dark matter. But here's the mind-bending twist. Neutrinos didn't just shape the past, they might still be shaping reality today. Every second, trillions of neutrinos from the sun pass through your body, oscillating as they go. In a way, you're bathed in the same quantum-deciding particles that forge the cosmos. Their oscillations a living relic of the universe's first irreversible choice. It's a humbling thought that the same particles now flitting harmlessly through your fingertips once held the reins of existence itself, their quantum dance the silent choreographer of everything. Imagine the universe's first moments not as a quiet quantum whisper, but as a roaring storm of plasma, a seething, white-hot soup where particles collided so violently that reality itself couldn't stay uncertain for long. This is the crux of the quantum decoherence in plasma theory, which suggests the universe's initial superposition didn't collapse because of some mysterious observer or cosmic algorithm, but because the sheer chaos of the primordial plasma ripped away the quantum blur, forcing reality to pick a side. At temperatures exceeding 1 trillion degrees, the early universe was denser than a neutron star, with particles packed so tightly that they couldn't move without slamming into each other. In ordinary conditions, quantum systems can maintain superposition. Think of Schrödinger's cat, both alive and dead, shielded from the outside world. But in this primordial maelstrom, there was no shielding. Every photon, quark, and electron was constantly buffeted by collisions, each interaction acting like a tiny measurement, chipping away at the universe's quantum uncertainty. It's like trying to balance a pencil on its tip during an earthquake. The environment is so disruptive that the pencil, or in this case, the universe's superposition, doesn't stand a chance. This relentless decoherence left its fingerprints in the cosmic microwave background, the afterglow of the Big Bang, those faint temperature variations we see mapped across the sky. They're not just random noise, they're quantum fluctuations from the universe's earliest moments, frozen in place when the plasma finally cooled enough for light to break free. The patterns aren't arbitrary. They're artifacts of how the plasma's turbulence amplified some quantum states while suppressing others, like a cosmic filter that only let certain vibrations through. But here's the twist. This theory doesn't just explain the past, it reshapes how we think about quantum mechanics today. If decoherence in plasma could collapse the universe's superposition, then the line between quantum and classical reality isn't as absolute as we once believed. It's not that the quantum world obeys different rules, it's just far more fragile, easily shattered by the right kind of chaos. That's why we don't see cats or cars in superposition. They're constantly bombarded by interactions, just like the primordial plasma, forcing them into definite states. Yet the most tantalizing implication lies in the shadows of the cosmic microwave background. Some physicists argue that if we look closely enough, we might find anomalies, regions where the plasma's decoherence was imperfect, leaving behind faint quantum echoes. These cosmic scars could hint at a deeper layer of reality, where the universe's first uncertainty never fully resolved, still shimmering beneath the surface of everything we know. So the next time you stare at static on an old TV screen, remember, you might be glimpsing the aftermath of the universe's first and most violent decision, the moment chaos tore the quantum veil and reality as we know it was born. The fabric of reality might not be smooth and featureless, it could be knotted, twisted into intricate loops and braids that lock the universe's first quantum states into place like cosmic shoelaces. This is the mesmerizing premise of topological quantum field theory, which suggests the universe's initial superposition wasn't resolved by random chance, but by the hidden geometry of spacetime itself, a geometry where higher dimensional knots dictated which quantum possibilities could survive. Picture the early cosmos not as a formless fireball, but as a labyrinth of tangled quantum fields, their paths weaving through extra dimensions we can't perceive, like threads stitching through the backside of reality. At the heart of this idea lies topology, the mathematical study of shapes that remain unchanged no matter how you stretch or twist them. A coffee mug and a donut are topologically identical because one can be deformed into the other without cutting or gluing. Now imagine quantum fields behaving like infinite, stretchy rubber sheets, vibrating in extra dimensions. As the universe cooled from its fiery birth, these fields didn't just settle randomly, they snagged on topological defects like a silk scarf catching on a rough edge. These defects weren't flaws, they were cosmic anchors, points where the fields became so twisted that they could no longer sustain superposition. The universe's first quantum ambiguity didn't fade, it was pinned down by knots tighter than any sailor could tie. The implications rewrite the rules of quantum mechanics. In ordinary physics, particles are points or waves, but in topological field theory, they're more like the intersections of braided spacetime. Electrons, quarks, even photons might not be independent entities, they could be the frayed ends of these cosmic knots, their properties determined by how many twists and loops they contain. This could explain why fundamental constants have the exact values they do. The topology of the early universe's quantum fields filtered out unstable configurations, leaving only the knots that could sustain complexity. It's as if reality were a vast game of cat's cradle, with the laws of physics emerging from which strings didn't tangle irreparably. But the real magic happens when you scale this up to the universe's birth. The Big Bang's quantum superposition might have been a frenzy of potential topologies, countless ways the fields could knot and braid until the mathematics of higher dimensions pruned the options. Some theorists suggest dark matter could be a relic of this process, particles trapped in topological pockets too deep to interact with ordinary matter. Even the cosmic microwave background's patterns might encode these primordial twists, like a fingerprint left by spacetime's first stitches. Where this theory gets truly radical is in its handling of time. If the universe's topology is fixed, then time's arrow might not be a fundamental property. It could emerge from the gradual unraveling of these quantum knots, like a sweater slowly fraying. Black holes could be where the knitting comes undone entirely. Their singularities not points of infinite density, but places where spacetime's braids snap and recoil into higher dimensions. And here's the haunting beauty of it all. If topological quantum field theory is correct, then the universe's first moment wasn't a blank slate. It was a loom weaving possibility into reality one knot at a time. Every particle, every force, every law we know might just be the echo of those first tight pulls, resonating across dimensions we'll never see but whose patterns are written into everything. The universe might not compute in the way we understand it could be computation itself, a vast quantum processor running on the fabric of spacetime. Quantum information theory proposes that every particle, every force, even the arrow of time itself, emerges from the manipulation of quantum bits, qubits, the fundamental units of quantum information. In this view, the Big Bang wasn't just an explosion of energy, it was the initialization of the ultimate quantum algorithm, with superposition acting as the first qubit state in a cosmic program still running today. Think of the early universe as a quantum computer booting up. In traditional computing, bits exist as zeros or ones, but qubits can be both simultaneously, an undecided state that unlocks exponential processing power. Now imagine this principle scaled to cosmic proportions. The universe's first moment wasn't a definite configuration of matter and energy. It was a vast array of entangled qubits, each one a thread in a computational tapestry weaving reality into existence. This quantum fog didn't hover passively, it processed. Every fluctuation, every interaction was an operation in a program so vast it birthed galaxies. The implications rewrite physics at its core. Gravity, electromagnetism, even the structure of spacetime itself might not be fundamental forces. They could be emergent behaviors, side effects of quantum information flowing and interacting. Black holes, for instance, might not just trap matter. They could be cosmic memory sinks, regions where information reaches maximum density before being scrambled and re-emitted as Hawking radiation. The speed of light, merely the processing speed of the universe's quantum circuitry, the maximum rate at which information can propagate through the system. This theory finds eerie support in quantum error correction. In quantum computers today, fragile qubits are protected from decoherence by spreading information across entangled states, a technique called quantum error correction. Now zoom out. The universe's own quantum states might be similarly protected. The cosmic microwave background's uniformity, the delicate balance of physical constants, even the persistence of matter over billions of years, all could be evidence of a built-in error correction protocol, ensuring reality doesn't crash despite quantum noise. But here's the most radical twist. If the universe is a quantum information processor, then superposition isn't a bug, it's the feature. Schrödinger's cat, neither dead nor alive, isn't a paradox, it's the system exploring all possible states before committing to one. Entanglements, spooky connections, just quantum data packets syncing across the cosmic network. Even dark energy's mysterious push could be the universe allocating more memory as it computes, expanding its processing space to handle increasing complexity. Critics argue this leans too heavily on metaphor, yet the math holds surprising predictive power. Quantum information theory accurately models black hole thermodynamics, and some versions of string theory map neatly onto error-correcting codes. The universe's initial quantum blur might not have been chaotic. It could have been optimally efficient, the first step in a computation whose final output includes every star, planet, and conscious thought that ever existed. And that raises a chilling possibility. If the universe is a quantum program, what or who wrote the code? Is there a cosmic coder beyond spacetime, or is the system self-booting, an eternal loop where each universe's output becomes the next one's input? The answer might lie in the superposition we've been chasing, not as a momentary glitch, but as the universe's first and most profound calculation, still running behind the scenes of everything we see. What if the universe didn't start with a bang, but with a perfect balance of opposites so exact that it all adds up to nothing? The zero-universe hypothesis dares to suggest that everything we see, every galaxy, every atom, even time itself, is just an elaborate fluctuation in an infinite void, a momentary ripple in the ultimate nothingness. Imagine a checkbook where every deposit has an equal withdrawal, where the grand total always reads zero. Now apply that to the cosmos, where every particle of matter is balanced by negative energy, every gravitational pull offset by cosmic expansion, until the sum total of existence is nothing at all. This isn't just philosophical wordplay, it's hard physics. Quantum field theory reveals that empty space isn't truly empty. It seethes with virtual particles popping in and out of existence, their fleeting lives governed by the uncertainty principle. Normally, these fluctuations cancel each other out instantly, but under extreme conditions they can tip the scales. Picture a calm ocean where every crest is matched by a trough, until one rogue wave rises just high enough to break the symmetry. The zero-universe hypothesis proposes that our entire cosmos is that rogue wave, a statistical outlier in the quantum foam where temporary imbalances spawned stars, planets, and consciousness before eventually collapsing back to equilibrium. The math behind this is eerily elegant. Einstein's equations show that the gravitational energy of the universe is negative, precisely counterbalancing the positive energy of matter and radiation. Even dark energy, the mysterious force accelerating cosmic expansion, fits the equation, its push perfectly tuned to cancel the pull of everything else. It's as if the universe is a cosmic Ponzi scheme, where all debts and credits miraculously balance, allowing something to emerge from nothing without breaking the bank of physics. But how does superposition fit in? In the beginning, this perfect zero wasn't a static state. It was a maelstrom of quantum possibilities, each fluctuation a potential universe with different laws, different dimensions, all summing to null. Most collapsed instantly, but our universe struck the delicate balance where the books could stay unbalanced just long enough for complexity to arise. That initial quantum blur wasn't random chaos, it was the void trying every possible combination to restore equilibrium, with our reality being the one temporary exception that stuck. The implications are staggering. If the zero-universe hypothesis is true, then existence itself is the ultimate free lunch, a self-canceling equation that requires no external creator or energy input. Black holes might be nature's way of balancing the books, their voracious appetites offsetting the universe's temporary positivity. Even the arrow of time could be an illusion, just the universe's slow unraveling back toward perfect zero, like a stretched rubber band snapping home. Yet the most poetic twist lies in the quantum foam itself. Those fleeting particles dancing at the edge of reality aren't just background noise, they're echoes of the universe's first and only real state, nothingness in its purest form. Every star, every thought, every moment of history might just be a glitch in the void's perfect balance, a shimmering mirage that, when viewed from far enough outside, never truly existed at all. From cosmic holograms to Boltzmann brains, from quantum time loops to universes born inside black holes, we've journeyed through staggering possibilities that stretch the very fabric of reality. Each theory isn't just a wild guess, it's a key turning the lock on existence, revealing how fragile our everyday notions of time, space, and even causality might truly be. Some ideas paint the universe as a grand computation, others as an infinite fractal or a self-correcting equation balancing to zero. Yet what unites them is their power to humble and exhilarate, reminding us that the cosmos is far stranger, far more dynamic than we ever imagined. So which of these visions feels closest to the truth? Does the participatory universe, shaped by observation, resonate with you, or does the holographic principle's illusion of reality strike a chord? Maybe you're drawn to the elegance of cyclic cosmologies, where universes rise and fall like breaths. There are no wrong answers here, only invitations to wonder. The beauty of quantum mysteries is that they refuse to fit neatly into any single box, forever nudging us to question deeper. This is just the beginning. The quantum rabbit hole goes further, branching into multiverses, time crystals, and realities where the past might rewrite itself. If today's theories left you hungry for more, stay tuned. We're only scratching the surface of existence's grandest riddles. Drop your favorite theory in the comments below, or tell us which idea bent your mind the most. The most thrilling part of science isn't having all the answers, it's the chase, the collective unraveling of a universe that always keeps one secret in reserve. Until next time, keep questioning, keep exploring, and remember, reality is almost certainly weird.